video, I'm going to find the mean and variance of a binomial probability distribution. We also are interested in finding the moment generating functions. So let's begin with first the form of the probability mass function for the binomial distribution. So we're going to go with f of x. The probability distribution function is given by n choose x, p to the x, q to the n minus x. Here, as you know, q is 1 minus p, and x, the number of successes, ranges from 0 to the number of trials. Okay, and of course the random variable x here is the number of successes in n trials. So the binomial distribution here has got parameters. Let me do it this way. We're going to assume the random variable x follows binomial with parameters np. Okay. Now, of course, the bound on p lies between 0 and 1, right? Because it's a probability statement. Now, we want to find the mean, the variance, and the moment generating function. Now, I'm going to go ahead and find the moment generating function first. Because once we have the moment generating function, it's a lot easier to find the mean and the variance of the binomial distribution. So, by definition of moment generating function, if you recall, mx, random variable x, the moment generating function is simply the expectation of e to tx, right? Which in the case of a binomial, we can write mx of t equals to, that would be the sum x from 0 to n, and of course e to tx times the probability distribution here is n choose x, p to the little x, and then q to n minus x. Okay. Now, what I'm going to do is actually I'm going to combine these into one expression, because remember, e to tx could be written as e to t to the x power. Okay, so we can actually combine what's inside of the sigma as, here's my combination notation, and what's going to be next is p, e to t, all of that to the power of x, and then q to the n minus x. And we recognize this latter summation as the binomial expansion of q plus p e to the t power to the nth power, right? That's what this summation ends up being. Now from this we can actually begin to, so there you go, that's the answer to the moment generating function. Now we're going to find, trying to attempt to find our expectation of x. So in order to do that, we need to do m prime at t of x. Okay, so that would be the derivative, the first derivative of the moment generating function that we're looking at. So that's going to be n q plus p e to t to the n minus 1 times chain rule, probability times p e to t. And from this I can actually factor in p and write this as np times e to t times q plus p e to t to the n minus 1 power. Okay, so that's what the first moment is. Now, expected value of x, which is the mean of the random variable x, is going to be m prime evaluated at 0, right? So I'm just going to put in 0 for t, and that's going to give me np times e to 0 times q plus p e to 0 to the n minus 1. Now, e to 0 is 1, of course, right? Inside parentheses, I'm going to get q plus p to the n minus 1. But then p plus q is going to be 1, isn't it? Probability of success plus probability of a failure is going to equal to 1. And in this case, So I'm going to get NP because what's in parentheses is going to be 1 to n minus 1, which is itself 1. So there you go. Therefore, the mean of the random variable is going to be NP. Okay. Now, in order to find the variance, I'm going to have to find the second moment and then use the second moment and the definition of the variance in order to find the variance. So now m double prime of t, okay, that's going to be, that's the derivative of the first derivative. So remember, the first derivative is up here, right? This is our first derivative of the moment generating function. So I'm actually taking this derivative, okay, of that expression. And when we do, this is what we're going to get. I'm going to get NP using the power rule here. Actually, what I did first, maybe I should copy this, but I'm looking at NP as a constant multiple and then using the product rule here, okay, of derivatives to find the derivative of the inside the bracket. So that's going to be NP times the derivative of inside, derivative of first times second, to the n minus 1, and then plus first times derivative of second, which is this one. The derivative of that's going to be n minus 1, and then q plus p e to t to the n minus 2, and then chain rule the derivative of the inside, which is going to be p e to t. Okay, and then so that's going to be the derivative. Now, in this, let's try to simplify this. If I look at this closely, well, I see e to t, and then this expression also is common somewhat, so we can actually factor those. Okay, and when we factor it, this is what we're going to get. We're going to get NP, and I'm removing q plus p. Oh, actually, I forgot. I'm going to bring out the e to t first, and then the binomial q plus p e to t, but I'm going to factor n negative 2. Okay, and negative 2. So when I factor that, that means inside I'm going to get q plus p e t, because these two, if you multiply those two binomials, you get exponent becomes n minus 2 plus 1, which is n minus 1, and that's what's there. Okay, so that's how you factor with negative exponent, or I should say not negative exponent, but exponent n minus 2. Okay, and then what are we going to have? Well, remember, from the second expression, I'm removing this, I'm removing the entire binomial, right? And all that remains is parentheses n minus 1, that, and then of course PET, p e to the t power. That's all that remains. True? Now, there you go. What do we do next? Let's work out inside brackets. So we get q plus p e to the t power n minus 2. Now, inside the bracket, I have q plus p e to the t power, and then distribute, I get n p e to the t power minus p e to the t power. And of course, we create a couple of opposites here. Those terms we can combine, and all said and done, now this would be the final version. NPE to t, and remember, we have the factor, the binomial in front. That's going to stay. And inside the bracket, we just have q plus NPE to t power. And that is the form of the moment generating function for the second derivative. That's the second moment, okay, of the random variable. Now we can actually find the variance. Now, if you recall the variance of the random variable x, let me write it this way. Sigma of random variable x is defined by expected value of x squared minus expected value of x quantity squared, which the latter one we usually write expected value of x as mu symbolically. Now, in order to find the expected value of x squared, that's going to be the second moment evaluated at 0. That's what expected value of x squared is that's the second central moment. Okay, minus mu squared, which we just found earlier, that was np, right? So, second moment at 0. So we're going to put a 0 in for t in this expression. Okay, so this becomes np, and then of course it's going to be e to 0 times q plus p e to 0 to the power of n minus 2 times q plus np e to 0. Okay, and then after this, e to 0 is 1, so this is simply going to become q plus p to the n minus 2, and then q plus np. Okay, and we can still simplify this one. Right? And let's see. Oh, let's see. Yeah, let's simplify this one. Now, remember p plus q is equal to 1, right? We know that. So this expression is simply 1. And 1 to any power is 1. So that the variance is going to be np times q, which is 1 minus p plus np. And there you go. That's what that is. And of course, we can distribute this over, or actually this is good enough. Let's leave it like that. And let's see. But that's just expected value of x squared. Okay, I need to do minus. That's minus np squared. Okay. Let me move that aside. So I have minus np quantity squared. There. I went ahead and attached square of the expectation. All right, and that's going to be negative n squared p squared once you raise it to a power. And then let's go ahead and distribute np times 1 minus p plus. I'm just going to move that expression out, distribute, and write it outside the parentheses. Minus n squared p squared. The reason obvious, because they're opposites. So that's going to be np 1 minus p. Therefore, we just showed that the variance of the binomial random variable is np1 minus p. And that's what we wanted to show. So again, in this video, we looked at the derivation of the formula for the variance of the binomial variable, random variable that is. We looked at the mean, and of course we looked at the moment generating function mx of t for the random variable x. And that concludes this video.